Hello everyone, thanks for coming to our mean curvature flow seminar again. This afternoon we're going to have Stepan talking to us. Stepan's from UQ. Originally I suggested he was going to talk about what happens for two-dimensional mean curvature flow inside R3, but he's actually told me he would like to continue talking about the Huisken-Sinestrari paper. So please take it away, Stepan.
Yeah, thank you, Tim. Yeah, actually, I just wanted to wrap up the paper in a few minutes, but when I started reading the paper, I realized there are 5 more sections to go, so it wasn't so easy to wrap up in a couple of minutes. So it's probably gonna take most of today's talk. And of course, there are plenty of things which I don't understand, so please feel free to interrupt me with any remarks, questions, whatever. Okay, so last time James defined this class of manifolds, CR alpha. It's just defined by some conditions. It's not really necessary. What are these conditions? Just some bound on 2 convex, mean curvature is bound from below, and the volume is bound from above. Maybe slight important note that this R right here is just a scaling parameter, and it can be chosen kind of arbitrarily. Okay, also what was shown by James last time is that the class CR alpha is preserved by mean curvature flow. So this is nice. This means that when we start with a manifold that is in this class, yeah, I guess I should mention our manifolds are immersed in Rn plus 1 for n greater than or equal than 3. The case n equals to 2 is somehow more difficult, but maybe we'll get to that towards the end of the talk. And also what was shown by James last time, that there are actually some surgery parameters. So there exist surgery parameters such that the class is preserved. Again, is preserved by, let's say, mean curvature flow with surgeries, provided that the surgeries are better than our surgery parameters chosen. Okay. Okay. I guess I'm gonna quickly mention 3 important estimates that are required to make this procedure work. So those are the convexity estimate, which is roughly that for each delta there exists C delta such that the lowest eigenvalue is bounded from below by the mean curvature times delta minus C delta. And this C delta depends on the initial hypersurface of the flow. So that's convexity estimate. Then there was the cylindrical estimate. Roughly, again, we are given some eta, and we're claiming that exists C eta, this time dependent on n alpha in the initial hypersurface, such that the second fundamental form, minus h squared over n minus 1, is bounded from above by eta h squared plus C eta. The cylindrical estimate. Oh yeah, that's what I want to do. By the way, of course, these are like vague statements. There are more assumptions which I'm not gonna make precise because, as I mentioned, I want to skim through 5 sections or so it's not gonna be very precise, but hopefully you get the idea how things are done. In the cylindrical estimates, this one is actually the one which fails. So there it's required the n is greater than or equal than 3. So this one is the one which needs to be replaced in the case when we are embedding surfaces into R3. And then there's the last one, which is the gradient estimate. Gradient. And this basically says that it just exists some gamma 2, gamma 3, depending again on n alpha and the initial hypersurface, such that the gradient of the second fundamental form can be bounded from above. Like that. So yeah. Okay. And I think there were nice questions last time. Well, if we know, this basically goes like this. So if we know that the class is preserved by mean curvature flow with surgeries, then these estimates works with surgeries as well. And the point is that this is actually not true. And that's why that's actually content of sections 3 to 6, basically. The point is that if we are given delta, the C delta depends on the initial hypersurface. And so C gamma, and so these gammas as well, C eta, sorry, and the gammas as well. So that's why we can perform surgery and we remain in the same class, but it might be necessary to find new constants that bound our quantities. So we would like to find such C delta, C eta, and gamma 2 and gamma 3, such that these estimates works for the whole mean curvature flow with surgeries, provided that the surgeries are sufficiently nice. Because a priori, we don't know which surgeries are we gonna perform, and thus we can just like do the surgeries beforehand and choose the maximum of this constant. We just want some uniform bound for all times. So that's, as I mentioned, that's the content of the section 3 to 6. So basically, just to sum up, given CR alpha, the class, there exist surgery parameters such that these estimates hold for mean curvature flow with such surgeries. Okay, does it make sense? Are there any questions? Okay, so if no, we would like to prove the main theorem of the paper, which is, I'm gonna make the statement a bit more precise in a minute, but roughly the statement is that mean curvature flow with surgeries terminates in finite time. Okay, so for this to work, I'm gonna state first important corollary. So it's corollary, it's 715 in the paper. The statement is as follows. So given MT, smooth mean curvature flow, this is without surgeries, again, of closed to convex hypersurfaces, and given some parameters epsilon KL, then there exists some bound, I'm going to call it H star, which depends on the initial hypersurface again, such that whenever we hit this bound. So by that I mean if the maximum of mean curvature, let's say at time t0 of our manifold, is greater than equal than h star, then one of two things happens. Either there exists epsilon k L neck, or MT0 is convex. All right. This is very useful corollary. It basically means that if we let our hypersurface evolve along the mean curvature flow, then if the mean curvature hits certain threshold, this h star, then there is a neck upon which we can do our surgeries, or the hypersurface is convex. And I think it was Adam probably in last semester who showed that if the mean curvature is if the hypersurface is convex, then it evolves into a round sphere and there is no problems anymore. So really what is of interest for us is that there exists this neck on which we can perform surgeries. So maybe two small remarks. This is actually about the propositions of this is corollary, of which this is a corollary. So first thing, there are actually two theorems, which this is a corollary, and they depend on the quantity lambda 1 over h. So if lambda 1 over h is small, that means that we are on a neck which roughly looks like this. And let's say somewhere is our P0, which is a point in which there is the high curvature, and it lies in the neck. So that's nice. And the other thing that can happen, that lambda 1 over h is not small, but still we have somehow hit high curvature. So what does this mean? Is that the neck is actually closing in the same speed that we are approaching the singularity. So this might be the case, for example, here's our P0, and it doesn't actually lie on some neck. But there's a nice lemma in this case, which actually doesn't have to do anything with mean curvature flow. It's just, it works general for hypersurfaces. And it claims that if this is the case, then there exists Q0 with, and Q0 such that the ratio at Q0 is small. So basically somewhere there is Q0 and we have a neck around Q0. This is, by the way, a difference with approach that Hamilton did with surgeries for Ricci flow, because this doesn't require any a priori bounds. It just works for hypersurfaces. And whenever we have a curvature high enough and lambda 1 over h is not small, then we can find some neck in the vicinity of P0. I'm gonna make a bit precise what I bit more precise what I mean by in the vicinity of P0. What I mean by that is that for every Q tilde, such that Q tilde is closer to P0 than our Q0, then the mean curvature at Q tilde is above some bound, which again is going to be important later. So I'm going to divide this by some gamma 0. This gamma 0 is not important. The point is that the neck happens, so this neck right here happens before the curvature drops too much. Okay. So this is how we can detect necks and actually make surgeries. Okay. So this sounds pretty good. We have a corollary that whenever the mean curvature is high enough, we actually have a neck and we can perform surgeries. This is amazing, but there are actually two small caveats for that. The first one is that we are actually assuming that the mean curvature is smooth. And this is useful in the first part. So in the proof that there exists a neck, if lambda1/h is small, we are actually using that there is some neighborhood where weren't surgeries before, or at least for some time. So after the first surgery, finding these necks is a bit more difficult, which I'm not going to get into, but it's possible to do. And secondly, and more importantly, this just ensures existence of a neck. This doesn't mean that we can perform surgery and somehow the quantities will be nice. So it doesn't, for example, mean that the mean curvature is going to drop below this H star after we perform the surgery, right? And it kind of makes sense, right? If we have some high curvature, like let's say here, and we're gonna perform a surgery, we're gonna basically put there a cap, and why this cap should have lower curvature, lower mean curvature? There's no reason, and in fact, it won't have. So the main idea of the proof of the main theorem is actually enlarge the neck far enough that the curvature drops, and we're gonna do the surgery there. So that's the rough idea. Now I'm gonna state the theorem and give you some details on how that works.
So Stepan, just a question. Yeah. Does this mean that you're never wanting to do surgery if you're in a vicinity of one of these caps?
Yes.
Okay. Thanks.
Never. Yeah, no problem. Okay. That's for the question. Okay, so now I'm gonna state the main theorem. If you're wondering, it's 8.1 in the paper. Okay, so assumptions as usual. We are given M0 in our class, CR alpha. It's 2 convex, n is greater than or equal than 3. It's immersed in Rn plus 1. And also we have control of the second fundamental form. But as I mentioned before, the condition right here can be arranged by scaling the R. It just basically just says we are choosing appropriate class for our manifold. Okay. And the claim is that then there exist 3 constants, H1, H2, and H3, such that the following hold. Or maybe such that there exist mean curvature flow with surgeries, such that, so first claim, the maximum mean curvature at the time of the surgery, TI are the times of the surgeries. So TI are surgery times. And by the minus here, I mean the time of the surgery before the surgery actually happens. So we're approaching from the left. So the maximum mean curvature at time of the surgery is H3. And maximum mean curvature at the time of the surgery after the surgery is smaller or equal than H2. So that's where we are using these 2 constants. And this is great because if we can, the fact that we can ensure that after each surgery, the maximum mean curvature drops from H3 to A2, which are not the same. This gives us a bound on the time between the surgery. between the surgeries, because the curvature kind of have to accumulate from H2 to H3. So there's actually a uniform bound between the surgery times. Okay.
Stepan, is it sorry if you said this already, but these numbers H1 and H2 and H3, independent of your initial surface?
Yeah, that's a bit tricky. I mean, as I'm stating it right now, they depend on the surface, but it's actually possible to find some values, omega 1, omega 2, omega 3, and then we have to just choose H1 bigger than omega 1, something like this. H2 must be omega 2 H1, and H3 I think can be anything bigger, but just to be sure, I'm just gonna write it like that.
So it really only depends on like R and alpha?
Yes, and these omega, exactly. They depend just on the class CR alpha.
Yeah, okay. Good, thanks.
I think they should be independent of alpha, sorry, of R even. They should be scaling invariant, shouldn't they? Or it should just come out as a scale factor again.
Yeah, I mean, I'm assuming that the second Farmer form is bounded by the R, so I think, yeah, I'm not sure, but yeah, it's just a scaling factor, so probably they are just dependent on alpha. I guess you're right.
Yeah.
Yeah, so just on alpha. Yeah. Thanks for the comment. Yeah, I'm just gonna delete this because, but yeah, this omega can be chosen just depending on alpha. Yeah, I think so. Okay, so the second claim is that the flow terminates in finite time and uses finitely many surgeries, basically. Okay, and the last property is that the surgeries are done on normal necks with mean radius. I'm gonna denote it R Z0 and -1 of H1. Okay, so this is where we are using the smallest mean curvature, and this reflects exactly what I was saying before, that we basically have somewhere big curvature which we're gonna get rid of. We're gonna find a neck nearby, and we're gonna continue the neck so far that the curvature drops to H1, where we can perform the surgeries and remove the regions with high curvature. Does it make sense? Is everyone happy with the statement? Okay. So I'm actually gonna state one more lemma before I get into the proof sketch, which I'm gonna maybe I'm gonna denote it theorem. So it can be called something like neck continuation, which is 8.2. Okay, so again, we are given some mean curvature flow with surgeries. And then we claim that if maximum mean curvature hits some, let's say at T0, hits some threshold, I'm gonna write H3 because that's the role this H is gonna play, but this is not consequence of the theorem. That's independent theorem that we need to prove before. But this is the same H3. So if the mean curvature, maximum mean curvature hits H3, and we have some point P0 on our manifold, such that the curvature, the mean curvature of P0 is greater than or equal than 10H1. This 10H1 is kind of a rough estimate of H2, basically. So it means just that the curvature is within H2 and H3. And the lambda on our P0 is small. Let's put it like that. Then there exists some neck n such that P0 is on our neck, which is good because we want to get rid of it because it has high curvature. And again, one of two things happens. So maybe, and either n is the whole surface empty, which may happen. This is exactly the case. We have something like Sn minus 1 times S1. So then our surface is kind of one big neck, and it covers everything. Or it ends with cross sections sigma 1 and sigma 2, such that again one of two things happens. So sigma i's are either boundary of a cap. By that I mean that the cap is actually on our surface. So something like maybe like this. So this is our neck, and this red line, oh, okay. This red line is my sigma. So it's a bound of this cap on our surface. Or the other thing that may happen, that mean radius of sigma is 2n minus 1 over h1, which means that our neck has enlarged and it's large enough so that again the sigma is large enough so that the curvature has dropped. And again, we're gonna perform our surgeries. Okay. Does that make sense? Any questions, comments? Okay, if not, then I'm gonna actually do this proof of the main theorem. And yeah, so I'm gonna do proof of main theorem, respectively. It's just sketch. Okay, so first part I'm gonna just skip right through. It's just a lot of work that was done in the sections 3 to 6. Is just choosing appropriate constants so that our estimates work, basically. All of these estimates. That's the bulk of the paper, and I'm not gonna get into that. But then when everything is set and done, and we have the H1, H2, and H3, we're gonna start our flow until we reach a point where the maximum mean curvature is H3. And when that happened, let's say we have some point P0 where the mean curvature is exactly between H2 and H3. Okay. So again, one of two things happens. So either the ratio lambda 1 to H is small at the point P0. That's good. We can apply neck detection, neck continuation lemma. Sorry, that's the lemma right here, and we're gonna obtain a neck such that it contains P0. Okay, so this is something like this. There's our P0 with high curvature. So that's nice. Or the ratio is not small. Well, but then we have a neck detection, which I mentioned before. So we are in this setting, and we can find the Q0 where the ratio is actually small. So there exists Q0 where the ratio is small. And again, we use neck continuation, this time from the Q0, to get a neck. So let's write it like that. There is, maybe I'm gonna use some colors. So this is Q0. There is P0. Okay. And I'm claiming that P0 is either in the neck in the first place, so that we can enlarge the neck so that it's in the so that P0 contains it, so that P0 is inside, or the cap, or we are in the situation that boundary is a cap, exactly as I write it here. So what I'm trying to say is that we are not in a situation like this, where there is our P0 and we have chosen this neck, which obviously is not what we want. So we can always choose neck like this. And why can we do that? Well, we know that there is neck around Q0. So if P0 is not in the neck, this is our sigma. So let's assume that we are not in this situation, that boundary is not a cap, and we are in this situation. Well, but if we are in this situation, it means that the mean curvature has dropped, and on this sigma, the mean curvature is small. Well, but that cannot be the case because, as I mentioned before, for every Q prime, which is closer than Q0, the curvature is high enough. That means we cannot be in this case because here the mean curvature is small, and we must be in this case, the boundary is a cap, and thus P0 is in our cap. Yeah, I'm not. Does it make sense? Have I explained it well enough, or should I say it again? I'm not sure if I just wasn't too confusing.
Oh, you could give it one more go, I guess. Not that it was bad, but as you say, it's hard.
Okay, so maybe I'm gonna state it a bit differently. So I'm gonna denote A, which is my neck, and I'm gonna attach all the caps if there are any. Of course, it might be the case that there are no such caps. So I mean that the boundary of D1 is sigma 1, boundary of D2 is sigma 2. And I'm basically claiming that P0 is in my A. So either it's in the neck, or it is in the cap we have at the end of our manifold, basically. So in the first case, I think it's pretty obvious, right? Because the neck continuation exactly tells us that P0 is in the neck. That's right here. And if we are in the second part, if the ratio is not small, we know there exists Q0 somewhere nearby. And by nearby, I mean in this sense, which I mentioned above, that whenever we are nearer than Q0, the curvature haven't dropped. So we make a neck around Q0, and I'm claiming that the P0 is actually in the cap, that is whose boundary is our sigma. So since I'm using neck continuation, I know that I must be in one of these two scenarios. So if I'm in the first scenario, I'm fine. P0 is in A because A includes the caps. And if I'm in the second scenario, that means that the curvature must have dropped before I have reached the P0. But this can't happen because for our neck detection, we are claiming that we can find Q so close that the curvature won't drop till we get to P0. Okay. So I hope this makes sense. If not, ask questions. But this is the main thing we want to look at. Because when we get that P0 is actually inside our region A, we're going to remove the A region shortly. And this means that we are actually removing the region when the curvature is too high. So that's exactly what we want to do. I guess one remark, the boundary of A has curvature approximately H1, right? Because we know that H1, we know that A, right here, defined right here, is just our neck N with some disks attached. So either the disk is attached and there is no boundary, which is this case, or we are in the second case of our lemma, and the radius is too high so that our curvature has dropped, and we have curvature comparable to H1. So that this exactly ensures that we can do the surgeries at our regions, at the boundary of our regions A. Okay. So now basically we repeat for every point on our manifold where, let's say at T1, such that the curvature at that point is between H2 and H3, and the point P wasn't selected yet. So P belongs to our manifold without A1, etc. And in this way, we trap each of our points with high curvature, with curvatures between H2 and H3 inside some region A. Okay, maybe I'm gonna denote this region A0, because it contains the point P0. And important note here is that the volume of any AI is actually bounded from below by some constants that depend on H2. This means that each of our regions is taking at least some fixed amount of volume, and therefore there are at the most finitely many such regions, because our manifold is closed, and therefore it has some volume. So there cannot be infinitely many regions, and thus we will not be performing infinitely many surgeries. Okay. So I hope this makes sense. So the next step is perform standard surgeries on color neighborhood of delta A, the delta AIs. Why we are doing it on color neighborhood is just to ensure that there is a part of our manifold that is not going to be changed. So maybe just a quick picture. So let's say we are in this setup. We have found this is our neck N. The region A is actually everything in here because there's a cap attached. And now we would like to do surgery right here, close to the boundary. It is, yeah, so assume that the green region has already small enough curvature so that we can perform surgery. It doesn't look like it from the picture, but that's the idea. Also, if it would happen, for example, that we have something like a dumbbell, and we have two regions, A1 and A2. So it may happen they actually share a boundary, like in this case. And when we are doing the surgeries somewhere close to the boundary, but not exactly on the boundary, we are ensuring that the surgeries don't interact with each other. Okay, so that's why we do it on the color. Okay, and now final remark. Well, okay, sorry. So we perform standard surgeries. The next step is to discard the AIs. So remember, whenever we had a point with high curvature, it was contained in some A. This is A0. So it was contained in some A. So after we have performed our surgery and we discard AIs, we are effectively getting rid of the points with high curvature. And since we are performing the surgery on regions where the curvature is approximately H1, then the new surface has maximum mean curvature bounded by H2. Okay. And furthermore, since there is a difference between H2 and H3, we can actually get, so there exists an estimate, there exists constant C, which depends on N, H2, and H3, such that the difference between surgery times is bounded from below by this constant. So this ensures that our algorithm is gonna end infinitely many steps, because whenever we are doing mean curvature flow, the volume drops. The volume is like making smaller, and also whenever we are removing some regions A's, we are discarding the AIs, we are getting rid of some volume. So that's why the flow is going to terminate in finite time. So this is kind of the end of the proof. So maybe just a small picture how this might look. So we can have something this I want. So we have some region here. Let's say there are a lot of holes. Something like this. Then there is a neck. Maybe another hole. and cap, something like this. Now we find regions with high curvature. This might be, for example, here and here and here, maybe, or maybe not the last one, whatever. We find necks nearby such that we can perform the surgeries in the columns. So these are A1 and A2. We perform the surgeries. So we're gonna end up this sort of surface. Then there is a sphere resulting from A1. Then there's gonna be some surface in between. And there's gonna be again a sphere from A2. Let me just do. So these are the points where we are doing the surgery. And these are the caps that we will attach afterwards. And now we get rid of the A's, which contain high enough surgery, and we let it evolve again via mean curvature flow. So for example, this Sn minus 1 times S1 is gonna soon hit some place with high curvature, and the neck is probably gonna be everything. So the A is gonna be the whole this region, the whole region, and we're gonna discard it altogether. Okay, so this is just a picture how the algorithm might work. Okay, so this is the idea of the proof. Are there any questions? Okay, so if not, I'm gonna state one nice corollary. So corollary, I think is 1.2 or something like that. So this statement is that for every smooth n-dimensional two convex immersed hypersurface in Rn plus 1. Again, n is greater than or equal than 3. So each such a manifold, let's call it M, is diffeomorphic to a connected sum of Sn minus 1 times S1 manifolds. So it's a connected sum of these manifolds. By the way, if the sum is empty, I just mean that our manifold is sphere. And the proof, it's not actually that straightforward, but it's basically just kind of backtracking the algorithm we have introduced. So each time we are removing, as you can see here, each time we are removing either a sphere or we're gonna remove this Sn minus 1 times S1. Something similar to a donut. Torus. Okay. And furthermore, the corollary even says that our manifold M is actually a boundary of some handle body. All right. Okay, so that's hopefully me finishing the Huisken-Sinestrari paper. It's 53, so I think it's not a good idea to start the surfaces in R3, but maybe just a quick remark, if there are no questions, that the problem is exactly the cylindrical estimate, and we need to introduce some new quantities to control the behavior of our surface. And also we need to do a new proof of gradient estimate, because the proof we had before is using cylindrical estimates. So, and we don't have those. So we actually need to compute these two estimates again. And that's the problem in n equals 2. Okay, yeah, I'm gonna leave it here. Thank you for your attention.
Awesome. Thanks for your words, Stepan. Let's thank our speaker.
Thanks, Stefan.
Problem.
Does anyone have any comments or questions they'd like to put to Stepan?
So this last statement about being the boundary of a handle body, that I guess that's in general, that's an immersed handle body, right?
Yes, I think so.
Yeah.
Yeah.
I guess you can strengthen it to say that it's isotopic to the standard embedded one, though. So even if you start off with an immersed one, is that right?
Isotopic. Okay. Yeah. Sounds plausible. Yeah.
Yeah, probably. I don't know, but probably.
I think there's a paper of Buzzano et al. That
Okay. Yeah.
does that, I think. And I think that's something that might not be true in 2 dimensions. Is that
Yeah.
is that right? I'm not sure of exactly the details.
Yeah, I'm not sure either.
If there are no other comments or questions, let's thank our speaker again.
Thanks, Stepan.
Awesome.
Nice talk.
Thanks all. I'll stop the recording there.